Hello, and thanks for joining. My name is Derek Kane, and today we're going to talk about time series forecasting concepts. This presentation is just one presentation in a broader series of lectures diving into topics of machine learning, data mining, predictive analytics, and statistics. If this topic interests you, or any topics in machine learning interests you for that matter, feel free to subscribe to my channel and check out the other videos. Okay, let's begin. The overview of topics that we're going to get into today are going to include the importance of time series in a business context. We'll get into some decomposition basics, such as time series components, additive versus multiplicative models. Then we'll jump into some time series forecasting techniques, and we'll get into some general modeling considerations, some of the modeling algorithms themselves, and then output interpretation and diagnostics. Afterwards, we'll get into a practical application example, and then as part of the practical application example, we'll talk about generalized least squares, or the maximum likelihood method. The importance of time series predictions cannot be understated from a business context. The ability to observe the development of an area of interest over time and make predictions based upon historical observations creates a competitive advantage within an analytics-based 21st century global business environment. For example, if the organization has the capability to better forecast the sales quantities of a product, they will be in a much more favorable position to structure procurement, optimize inventory levels. This can result in an increased liquidity of an organization's cash reserves, decrease of working capital, and improved customer satisfaction through increased order fulfillment and decreased back orders. Additionally, the senior management can formulate the entire capacity planning, fiscal sales budget of the organization through better prediction of revenue, including cost and profit margin. Headcount, CapEx, and R&D expenditures, marketing budgets all rely heavily upon having a proper sales budget, and time series predictions are the backbone of a successful organization. I'm not going to get into too much of the business aspects here moving forward. We're really going to talk about the actual techniques of time series predictions and how to use them correctly. If you want to understand more of a business example and how to use this, feel free to go to the first presentation and the practical example that we went through, which will talk in detail about how we can leverage time series in financial planning purposes. But with that said, let's actually talk and get into time series and how to use them correctly. The first topic we're going to look into is decomposition basics, and this is a fundamental concept in working with time series data. So we have to have an innate understanding of how this works in order to really use time series methods correctly. Before we begin, I want to get briefly into the concept of looking at graphs critically and evaluating what we see in the patterns. Humans naturally see patterns in the data. We're a visual creature to begin with. But when we're talking in the context of being a data scientist or an analytical professional, we have to interpret these graphs differently. And we need to think about time series in a different context in order to really master these techniques. So whenever you're looking at these graphs, just think of it from a more analytical perspective. When we analyze a time series chart, and we start to look at this chart on the right-hand side, we need to begin to think about decomposing the chart into its basic building blocks, and then determine what type of time series model we're trying to model in this case. This process needs to be performed with every time series predictive task to ensure that we pair up the appropriate analytical model that best suits the data. It's not like we can say, okay, I'm working on time series, therefore I'm going to pull out this particular model and it's going to be a one-size-fits-all. I'm just going to run it through my time series algorithm and boom, I'm going to have my predictions. We have to really understand how to pair the right model with the right time series data. So I want to talk a little bit about the basics of decomposition. In the previous example, we can take that graph and we can break it into these fundamental components. So at the top, we actually see what the graph looks like. But if I begin to peer through the noise and start to look at the components that are within, I see that there's a trend component, a seasonality component, and then there's attributes beyond that general trend and seasonality that we call random fluctuations. One of the most important concepts when working with time series and decomposition is the concept of seasonality. Seasonality, or seasonal effects, is a systematic and calendar-related effect. Some examples include the sharp escalation in most retail series, which occurs around December in response to the Christmas period, or an increase in water consumption in summer due to warmer weather. So these are processes that have a natural spike or decrease due to a regular interval throughout the time of the year. Other seasonal effects include trading day efforts. The number of working or trading days in a given month differs from year to year, which will impact upon the level of activity in that month. And moving holidays. The timing of holidays, such as Easter, varies, so the effects of the holiday will be experienced in different periods each year. Seasonal adjustment, on the other hand, is the process of estimating and then removing from a time series influences that are systematic and calendar related. Observed data needs to be seasonally adjusted, as seasonal effects can conceal both the true underlying movement in the series as well as certain non-seasonal characteristics which may be of interest to analysts. Seasonality in a time series can be identified by regularly spaced peaks and troughs, which have a consistent direction and approximately the same magnitude every year relative to the trend. And this is an important idea that when we're looking at the seasonal components. Seasonality arises from systematic, calendar-related influences such as natural conditions, weather fluctuations that are representative of the season. So snow removal could be one example of a natural condition, or hurricane season. Business and administrative procedures, for example, the start and end of a school term. Social and cultural behavior, such as a holiday for religious purposes, as Christmas is. And calendar-related effects. And as we talked about, the trading day effects, which are the number of occurrences of each day of the week in a given month, will differ from year to year. For example, if there are 4 weekends in March in 2000, but 5 weekends of March in 2002. And also this would include the moving holiday effects, which would be like Easter, which occurs on a different day depending on the year. Another aspect with decomposition is the trend and irregular components. A trend can be defined as a long-term movement in a time series without calendar-related and random irregular effects, and it's a reflection of the underlying level. The irregular component, sometimes known as the residual, is what remains after the seasonal and trend components of a time series have been estimated and removed. It results from short-term fluctuations in a series which are neither systematic nor predictable. In a highly irregular series, these random fluctuations can dominate movements, which will mask the trend and seasonality. The seasonal, trend, and random components can be combined traditionally in two major manners to match the total observed data. It can be combined additively, which is the implicit assumption is that the three components are combined in an additive fashion to match the data. So I take my data, I take my seasonal component, plus my trend component, plus my random fluctuation, and that matches the data. Alternatively, we can look at it in a multiplicative sense, which is the implicit assumption that the three components are combined in a multiplicative fashion, which is I take the data, and it's the seasonal times the trend times the random component. The underlying question that we have here now is, do I take a multiplicative or additive approach to the data? Well, the time series techniques we will discuss are approached from an additive standpoint. Fortunately, multiplicative models are equally easy to fit to the data as additive models. The trick to fitting a multiplicative model is to take the logarithms of both sides of the model. So I take the log of data equals the log of seasonal times trend times random. After taking the logarithms, either natural logarithms or the base 10 logarithms, the three components of the time series again act additively. It is important to recognize when multiplicative models are appropriate. However, fitting the models is no harder than fitting additive models. This is important because when we're looking at constructing the approach, we want to approach it from an additive perspective. So before we dive into the topic of additive models, I want to give a very simple multiplicative example so we can understand when to use this type of model versus an additive approach. In many time series involving quantities, such as stock price movement, money, wheat production, the absolute differences in the values are of less interest and importance than the percentage changes. And when this happens, this is the scenario where a multiplicative approach would be used. So if I want to understand the percentage change of movements, multiplicative approaches are more appropriate than additive. In many time series, the amplitude of both the seasonal and irregular variations increase as the level of trend rises. As the underlying level of the series changes, the magnitude of seasonal fluctuations varies as well. This shows characteristics of a multiplicative modeling approach. So as trends are building, we see the peaks and troughs shifting with the trend components, and these are characteristics indicative of multiplicative time series models. Now that we've addressed the concept of an additive approach to time series, let's look at some forecasting techniques. Before we begin on this, let's talk about a general approach for analysis. First is we identify through a visual inspection whether the data has seasonality or trends. Okay, this is important. Then we identify whether the decomposition technique required is additive or multiplicative. If it is multiplicative in nature, let's do a log transformation. Then we're going to test an appropriate additive algorithm for our time series. Okay? And there are many different techniques that we're looking at, and we'll get into these topics in a moment, but look at the seasonal, look at the trend, and look at the random fluctuations. If there is no seasonal component, but there is a trend component, and there are no correlations in the data, well then a simple moving average smoothing method is appropriate. If we see that there's a seasonal component and there is a trend component, but there are no correlations in the data, well then seasonal adjustment. Likewise, with a simple exponential smoothing method, if there's no seasonal component, but there is a trend component, and no correlations, well then this is the method that we would use. We can continue to go on with Holts-Exponential Smoothing. So there is no seasonal, but there is a trend and no correlations. This is a technique that is applicable to that type of task. Holt-Winters exponential smoothing works when we have a seasonal and a trend, but no correlations. And finally, another topic is an ARIMA model, which can be used when we have a seasonal, a trend, and correlations in the data. So by looking at the data set and then performing some certain tests, that gives us a clue of what the appropriate time series model is to use. And we have to do this before we can properly apply the technique to our data. Afterwards, we're going to perform some statistical tests to verify that the correct model has been selected. Okay. We'll use the Legendre box test. We'll forecast the errors, making sure that our distributions are normal, we have a mean of 0, and a constant variance, which we had talked about in previous lectures. Then we'll get into the idea of an autocorrelation function, or a partial autocorrelation function, which are called ACF and PACF respectively. After we've done this, then we're going to repeat steps 3 and 4 if necessary. So if we use a model and it turns out that it doesn't have the right statistical fit, then we're going to go back and we're going to try a different method until we found the right combination that works for us. The first method that we're going to talk about is going to be the simple moving average smoothing. So what is a simple moving average smoothing of a time series? It's used to estimate the trend component of a non-seasonal time series, which consists of a trend component and an irregular component. And it can be described using an additive model. It's common to use a smoothing method, such as calculating the simple moving average of a time series. And what we're going to do is we're going to look at a time series called the Age of King's Death. And these are for successive kings in England, starting with William the Conqueror. And on the y-axis, we're going to see age in years, and on the x-axis, we're going to see the number of kings. So, as each king is living, we're going to find the age in which that they had died. This data set, when we look at it, it doesn't seem to show any seasonality or trending. However, the random fluctuation in the data are roughly constant in size over time. So just by looking at this data, we see no discernible pattern or trending, but we do see the random fluctuation is somewhat consistent. This essentially suggests to us that an additive model could be used to describe the data set. So by visually looking at the line graph in this case, we can make some reasonable assumptions that an additive model will work. So to use a simple moving average smoothing of time series, we're going to use a moving average of the order of 3, which is a MA3. When we do this, there still appears to be quite a lot of random fluctuations in the time series smooth using a simple moving average of order 3. Thus, to estimate the trend component more accurately, we might want to try smoothing the data with a simple moving average of a higher order. So the more the increase in the moving average order that we're using is it's going to start to smooth out these components until we just see just the area of interest. Okay. This process takes a little bit of trial and error to find the right amount of smoothing. For example, we can try using a simple moving average of the order 8. The data with a simple moving average of order 8 gives us a clearer picture of the trend component. So now we can actually see the shape of the trend over time a little more clearly. We can see that the age of death of English kings seems to have decreased from about 55 years old to about 38 years old during the reign of the first 20 kings. And then it increases after that to about 73 years old by the end of the reign of the 40th king in the time series. And this is clearly seen in the data. Now we're going to dive into the topic of a seasonality adjustment. So we're going to decompose seasonal data and seasonally adjust it. In our example here, we're going to look at the number of births per month in New York City. And the y-axis is going to be the actual number of births, and then the x-axis we're going to have the time in months. The dataset shows a seasonal variation with a number of births. There seems to be a peak in every summer and a trough in every winter. The seasonal fluctuations are roughly consistent in size over time, and random fluctuations are roughly constant in size. And this suggests that an additive modeling method could be used to describe the data set. Before we begin on this, let's really take a look at this data set. We can see that there is a general upward trend over time. So at first, we see a large dip, and then it systematically builds up over time. So that's what I would expect to see in the trend component. The seasonality, which is kind of the heartbeat shape in this case, we can see high peaks and low troughs. It's readily visible here. But if you look at some of the peaks and some of the troughs, we see a lot more like little squiggles in the line. And those squiggles are the irregular components of it. So when we're looking at this data set, just try to visually imagine what those three components are whenever you're working with time series. And the plot above shows the original time series. the estimated trend component, which is second from the top, the estimated seasonal component, which is third from the top, and the estimated irregular component, which is at the bottom of this case. So we've decomposed our additive time series into these three measures. And we see that the estimated trend component shows a small decrease from about 24 in 1947 to about 22 in 1948, followed by a steady increase from then on to about 27 in 1959. If you have a seasonal time series that can be described using an additive model, you can seasonally adjust the time series by estimating the seasonal components and subtracting the estimated seasonal component from the original time series. So we take our seasonally adjusted, which is our original, minus our seasonal component. And we can see that the seasonal variation has been removed from the seasonally adjusted time series. The seasonally adjusted time series now just contains the trend component and an irregular component. So by looking at this graph, we have now removed that seasonal pattern from the data. We will now shift gears and talk about a simple exponential smoothing method. Now let's dive into a simple exponential smoothing example. Here is a data set which contains the total annual rainfall in inches for London from 1813 to 1912. On the y-axis, we have our rainfall, and on the x-axis, we have our months. We can see from the plot that there is roughly constant level. The mean stays constant at about 25 inches. And if we look at this graph, we can imagine putting in a line for 25 inches across the horizontal in this case, and we'd see that all the peaks and troughs would kind of cut through this line in the middle. Okay. The random fluctuations in the time series seem to be roughly constant in size over time, so it is probably appropriate to describe the data using an additive model. If we have a time series that can be described using an additive model with constant level and no seasonality, you can use a simple exponential smoothing to make short-term forecasts. The simple exponential smoothing method provides a way of estimating the level at the current time point. Smoothing is controlled by the parameter alpha for the estimate of the level at the current time point. The value of alpha lies between 0 and 1. Values of alpha that are close to 0 mean that little weight is placed on the most recent observations when making forecasts of future values. So in R, if I run the Holt-Winters simple exponential smoothing, I see what my smoothing parameter, in this case, I see what my alpha level is. And what the output in R is telling us is that the estimated value of the alpha parameter is about 0.024. This is very close to 0, which tells us that the forecasts are based on both recent and less recent observations, although somewhat more weight is placed on recent observations. The plot shows the original time series in blue and the forecasts as a red line. The time series of forecasts is much smoother than the time series of the original data here. As a measure of the accuracy of the forecast, we can calculate the sum of squared errors for the in-sample forecast errors, which is the forecast errors for the time period covered by our original time series. It is common in simple exponential smoothing to use the first value in the time series as the initial value for the level. For example, in the time series for rainfall in London, the first value is 23.56 for rainfall in 1813. So when we run our Holt-Winters technique, we see that the L.start parameter in the R model, we're defining 23.56. But when we look at this chart, we see that the line is almost a straight line that cuts through in the middle. So between our actual observed and what we're predicting in this case, there's going to be a very large variation using this technique. Here, the forecasts for 1913 to 1920 are plotted as the red line. the 80% prediction interval as the area between the maroon dotted lines. The forecast errors are calculated as the observed value minus the predicted values for each time point. Of course, we can only calculate the forecast errors for the time period covered by our original time series, which is from 1813 to 1912 for the rainfall data. So we can't calculate errors when we're forecasting in the future because we haven't observed them yet. And this data set doesn't show the data beyond 1912. What are some statistical tests that we can use to improve upon this model? If the predictive model cannot be improved upon, there should be no correlations between forecast errors for successive predictions. In other words, if there are correlations between forecast errors for successive predictions, it is likely that the simple exponential smoothing forecast could be improved upon by another forecasting technique. To figure out whether this is the case, we can obtain a parallelogram, or an ACF, of the in-sample forecast errors for lags 1 to 20. We can see from the sample parallelogram that the autocorrelation at lag 3 is just touching the significant bounds. So these significant bounds, these dotted lines, we're looking for breaches that are crossing that threshold in this case. And in this example, we see that it breaches, or it gets very close, right at lag 3. Now we're going to conduct the Legendre box test, and the test statistic is 17.4, and the p-value is 0.6 for this model. When we run this, this gives us little evidence of non-zero autocorrelations in the in-sample forecast errors at lags 1 to 20. So by actually typing this into our console and specifying that lag of 20 and running this Legendre box test, we can find out that there is little evidence of non-zero autocorrelations in the in-sample forecast. So to be sure that the predictive model cannot be improved upon, it is also a good idea to check that the forecast errors are normally distributed with a mean, zero, and constant variance. To check whether the forecast errors have constant variance, we can make a time plot for the in-sample forecast errors. The plot shows that the in-sample forecast errors seem to have roughly constant variance over time, although the size and fluctuations in the start of the time series may be slightly less than at later dates. So when we're looking at this, we're just looking to see, much like a residual plot in linear regression, that the peaks and troughs are kind of randomly dispersed across the forecast series. Constant variance can be detected by looking at the peaks and troughs to see if they're moving evenly above and below this zero horizon. To check whether the forecast errors are normally distributed with a mean of 0, we can plot a histogram of the forecast errors with an overlaid normal curve that has a mean 0 and the same standard deviation as a distribution of the forecast errors. The plot shows that the distribution of forecast errors is roughly centered on 0 and is more or less normally distributed, although it seems to be slightly skewed to the right compared to a normal curve. However, the right skew is relatively small, and so it is plausible that the forecast errors are normally distributed with a mean of 0 in this case. So overlaying the normal distribution against the histogram gives us an idea of whether or not this violation has been, or this assumption has been violated. So our conclusion is that the Legendre box test showed that there is little evidence of non-zero autocorrelations in the in-sample forecast errors, and that the distribution of forecast errors seems to be normally distributed with a mean of 0. This suggests that the simple exponential smoothing method provides an adequate predictive model for London rainfall, which probably cannot be improved upon. So we've looked at the data, we decided what tool to use, then from this tool we ran a series of tests in this case and decided that this particular model was most appropriate to fit the data. Now let's shift gears and we'll talk about the Holts-Exponential Smoothing technique. First, let's take a look at a data set. An example of a time series that can probably be described using an additive model with a trend and no seasonality is a time series of the annual diameter of women's skirts at the hem from 1866 to 1911. So when we look at this graph, on the y-axis we have the diameter of skirts, and on the x-axis we have time in months. We can see from the plot that there was an increase in hem diameter from about 600 in 1866 to about 1050 in 1880, and then afterwards the hem diameter decreased to about 520 in 1911. So as we're looking at skirts and the fashion in the time, we see this general trend increase where we have these wider hems, and then over time we find that they kind of fall out of fashion and then they decrease. If we have a time series that can be described using an additive model with increasing or decreasing trend and no seasonality, we can use Holts-Exponential Smoothing to make short-term forecasts. Holts-Exponential Smoothing estimates the level and slope at the current time point. Smoothing is controlled by two parameters, alpha for the estimate of the level at the current time point and beta for the estimate of the slope b of the trend component at the current time point. As with simple exponential smoothing, the parameters alpha and beta have values between 0 and 1, and values that are close to 0 mean that little weight is placed on the most recent observations when making forecasts of future values. To make forecasts, we can fit a predictive model using the Holt-Winters function in R. To use Holt-Winters for Holts-Exponential Smoothing, we need to set the parameter gamma equals false. The gamma parameter is used for Holt-Winters exponential smoothing as described below. For example, to use Holts-Exponential Smoothing to fit a predictive model for the skirt hem diameter, we type in our Holt-Winters skirt series and then outright specify gamma equals false. The estimated value of alpha in this example is 0.84 and beta is 1. These are both high, and that tells us that both the estimate of the current value of the level and of the slope b of the trend component are based mostly upon very recent observations in the time series. This makes good intuitive sense, since the level and the slope of the time series both change quite a lot over time. The value of the sum of squared errors for the in-sample forecast errors is 16,954. So when we look at the shape of this graph and we see that it looks like a roller coaster and it's constantly evolving, what we're finding is that the alpha and beta values being close to 1 in this example are looking at closer observations, more recent observations, when it's making its projection moving forward. And this makes sense when we look at the data. We can plot the original time series as a brown line with the forecasted values as a red line on top of it. We can see from the picture that the in-sample forecasts agree pretty well with the observed values, although they tend to lag behind the observed values just a little bit. So by looking at our graph in this example, we find that this exponential smoothing method works rather well. And it is common in this case to set the initial value of the level to the first value of the time series. So 608 for the skirts data, and the initial value of the slope to the second value minus the first value, 9 for the skirts data. So we initialize it based off of the initial starting observations. And we can see the R code down below that shows the L start and the D start with such parameters. The forecasts are shown as a yellow line with the 80% prediction intervals. So if I'm looking at this data developed over time, it looks a little more compact because of the size of the prediction intervals in this example, but it's the same data that we had. We can see the development of our red line and the possible errors in there, or our confidence at the 80% level. And as for simple exponential smoothing, we can make forecasts for future times not covered by the original time series by using the forecast.Holt-Winters function in the forecast R package. So for example, our time series data for skirt hems was from 1866 to 1911, and we can make predictions from 1912 to 1930, which are 19 more data points. Now, I specified 19 data points in the example. I mean, we can forecast however far out we want to go in this case, but and we're not necessarily limited. However, when working with time series and just predictive analytics in general, the further out we go from our prediction, the less likely our predictions are going to be correct. That's why we see the ballooning effect of our 80% prediction intervals in this case, because it just becomes more uncertain. We just don't know. Let's talk about some statistical tests that we can use to continue to improve upon this model. As for simple exponential smoothing, we can check whether the predictive model could be improved on by checking whether the in-sample forecast errors show non-zero autocorrelations at lags 1 to 20. Here is the parallelogram, which shows the sample autocorrelation for the in-sample forecast errors at lag 5 exceeds the significance bounds. However, we would expect 1 in 20 of the autocorrelations for the first 20 lags to exceed the 95% significance bound by chance alone. So when we run our ACF function and we have our bounds, our dotted lines in this case, we're looking for breaches, and in 20 lags we would expect one of them to breach surely by chance alone. But since they all fall within that range, for the most part, we can say that that autocorrelation is not an issue here. As for simple exponential smoothing, we can check whether the predictive model could be improved upon by checking whether or not the in-sample forecast errors show non-zero autocorrelations at lags 1 to 20. For example, for the skirt hem data we're looking at, we can make a parallelogram and then carry out the Legendre box tests by typing the following. Despite having the lag equal 5 exceed the significant bounds, when we carry out the Legendre box test, the p-value is 0.47, indicating that there is little evidence of non-zero autocorrelations in the in-sample forecast errors at lags 1 to 20. As for simple exponential smoothing, we can also check that the forecast errors have constant variance over time and are normally distributed with a mean of 0. The forecast errors appear to exhibit constant variance over time, and we can see the peaks and troughs, kind of dancing around this middle on the residuals. The time plot of forecast errors shows that the forecast errors have roughly constant variance over time. The histogram of forecast errors show that it is plausible that the forecast errors are normally distributed with mean of 0 and constant variance. Therefore, our conclusion is that the Legendre box test shows that there is little evidence of autocorrelations in the forecast errors, while the time plot and histogram of forecast errors show that it is plausible that the forecast errors are normally distributed with a mean of 0 and constant variance. Therefore, we can conclude that Holts-Exponential Smoothing provides an adequate predictive model for skirt hem diameters, which probably cannot be improved upon. So, as before, we run these statistical tests just to make sure that the model that we're applying in fact works correctly, and because it passed these statistical tests, we can draw some conclusions on that. Now we're going to move into the topic of Holt-Winters exponential smoothing. Let's take a look at the following sales. In this example, these are monthly sales for a souvenir shop at a beach resort town in Queensland, Australia. So the y-axis is the number of souvenirs that have been bought, and the x-axis is the time in months. In this case, it appears that an additive model is not appropriate for describing the time series, because the size of the seasonal fluctuations and random fluctuations seem to increase with the level of the time series. And that's important. So when we're looking at the time series, we have to make some assessments in terms of the general shape and trend in this case, and because it increases almost exponentially in this case, that additive models don't seem to make a whole lot of sense in this case. As a result, we may need to adjust this multiplicative time series in order to get a transform time series that can be described using an additive model. For example, we can transform the time series by calculating the natural log of the original data. When we transform the time series by calculating the natural log of the original data, we get the graph on the right-hand side. And by looking at this graph, we see that it no longer has this giant exponential growth pattern, that it's actually a little more consistent with the other data sets that we've been looking at. We can see that the size of the seasonal fluctuations and random fluctuations in the log transform time series seem to be roughly constant over time, and they don't depend on the level of the time series. So this log transform time series can probably be described using an additive model. This chart can be described as having an increasing or decreasing trend in seasonality. If we have a time series that can be described using an additive model with increasing or decreasing trend in seasonality, we can use the Holt-Winters exponential smoothing to make short-term forecasts. Holt-Winters exponential smoothing estimates the level, slope, and seasonal component at the current time point. Smoothing is controlled by three parameters, alpha, beta, and gamma, for the estimates of the level, slope B of the trend component, and the seasonal component, respectively, at the current time point. The parameters alpha, beta, and gamma all have values between 0 and 1, and the values that are close to 0 mean that relatively little weight is placed on the most recent observations when making forecasts of future values. To make forecasts, we can fit a predictive model using the Holt-Winters function in R. The estimated values of alpha, beta, and gamma are 0.41, 0.00, and 0.96 respectively. The value of alpha 0.41 is relatively low, indicating that the estimate of the level at the current time point is based upon both recent observations and some observations in the more distant past. The value of beta is 0, indicating that the estimate of the slope B of the trend component is not updated over the time series, and instead is set equal to its initial value. This makes good intuitive sense, as the level changes quite a bit over the time series, but the slope B of the trend component remains roughly the same. In contrast, the value of gamma, 0.96, is very high, indicating that the estimate of the seasonal component at the current time point is just based upon very recent observations. As for simple exponential smoothing and Holt's exponential smoothing, we can plot the original time series as a brown line with the forecasted values as a blue line on top of that. We see from the plot that Holt-Winters exponential method is a very successful method in predicting the seasonal peaks, which occur roughly in November every year. So just the shape of the line seems to mimic what we see in the data set very well in this case. The forecasts are shown as a blue line, and the red dotted lines show the 80% prediction intervals. I know it's not the easiest to see in this particular example, but we can see the trending and the seasonality components being picked up by this model. So as we are looking at the data series and as the trending is moving up, we see that the model has actually captured that data rather well. So we can continue to evaluate this approach by performing our statistical tests. In this case, the parallelogram shows that the autocorrelations for the in-sample forecast errors do not exceed the significance bounds for lags 1 to 20. So they all fall within these bounds. We can investigate whether the predictive model can be improved upon by checking whether the in-sample forecast errors show non-zero autocorrelations at lags 1 to 20, by making a parallelogram and carrying out the Legendre box test. When we run the Legendre box test, in this case, the p-value is 0.61, indicating that there is little evidence of non-zero autocorrelations at lags 1 to 20. We can also check whether the forecast areas have constant variance over time. So we're going to plot our residuals, and we're going to look at the spread of residuals across the zero. The forecast errors appear to exhibit constant variance over time. From the histogram of the forecast errors, it seems plausible that the forecast errors are normally distributed with a mean of 0. Our conclusion is that there is little evidence of autocorrelation at lags of 1 to 20 for the forecast errors, and the forecast errors appear to be normally distributed with a mean of 0 and a constant variance over time. This suggests that Holt-Winters exponential smoothing provides an adequate predictive model of the log of sales at the souvenir shop, which probably cannot be further improved upon. Furthermore, the assumptions upon which the prediction intervals were based are probably valid. So we've found a good model that fits this data very well. Now we're going to switch gears, and we're going to talk about ARIMA models, or autoregressive integrated moving average models. Exponential smoothing methods, which are the methods that we've discussed earlier, are useful for making forecasts and make no assumptions about correlations between successive values of the time series. However, if we want to make prediction intervals for forecasts made using exponential smoothing methods, the prediction intervals require that the forecast errors are uncorrelated and are normally distributed with a mean 0 and constant variance. While exponential smoothing methods do not make any assumptions about correlations between successive values of the time series, in some cases we can make a better predictive model by taking correlations in the data into account. This is what an ARIMA procedure does, or autoregressive integrated moving average includes an explicit statistical model for the irregular component of a time series. It allows for non-zero autocorrelations in the irregular component. ARIMA models are defined for stationary time series. Therefore, if you start off with a non-stationary time series, you will first need to difference the time series until you obtain a stationary time series. If you have to difference the time series d times to obtain a stationary series, then you have an ARIMA PDQ model where d is the order of differencing used. For example, the time series of the annual diameter of women's skirts at the hem from 1866 to 1911 is not stationary and mean, as the level changes a lot over time. So if we're looking at this data, it kind of looks like a roller coaster. It's constantly evolving. This is what the original data set shows. However, if I take a differencing of 1, the resulting time series of the first sequences does not appear to be stationary in the mean. It still kind of looks like its overall shape, but we see that there's a very high peak that starts on the top, and then when we go down to further observations, we see it begins to dance around the mean, but really most of them are below the mean. So the differencing of 1 does not appear to be stationary in this case. The time series of second differences does appear to be stationary in mean and variance, as the level of the series stays roughly constant over time, and the variance of the series appears roughly constant over time. So by shifting from a difference of 1 to 2, when we do a difference of 2 in this case, we see this pattern on the data. And this pattern now seems to be a little more of what we would expect of a residual plot. If we need to difference our original time series data d times in order to obtain a stationary time series, this means that you can use the ARIMA PDQ model for your time series, where d is the order of difference used. For example, for the time series of the diameter of women's skirts, we had to difference the time series twice, and so that the order of difference in d is 2. That means that we can use an ARIMA P 2Q model for our time series. The next step is for us to figure out the values of P and Q for the ARIMA model. I want to just take a look at the differencing again when we're looking at our original data set. Then when we see a differencing of 1 being applied and difference of 2 being applied. So we see that the data is transforming and it's melding across this line. And so by looking at the actual differencing functions, we can see how the patterns are emerging and how we can use this for defining what variables to include in the ARIMA model. Another differencing example that we'll look at is from the time series of the age of death of successive kings in England that we looked at earlier. So if you remember this data, it appeared to be almost random in terms of its pattern. However, if we do a differencing of 1 in this case, we actually find that a difference of 1 seems to fit the data very well. The time series of first differences appears to be stationary in mean and variance, and so probably an ARIMA P1Q model is probably appropriate for the time series. By taking the time series of the first differences, we have removed the trend component of the time series of the ages at death of the kings, and we're left with the irregular component. We can now examine whether there are correlations between successive terms of this irregular component. If so, this could help us to make a predictive model for the ages at deaths of the kings. How do we go about selecting a candidate ARIMA model? If our time series is stationary, or if we've transformed it to a stationary time series by differencing d times, the next step is to select the appropriate ARIMA model, which means finding the values of most appropriate values of P and Q for an ARIMA P to Q model. To do this, we need to examine the parallelogram and the partial parallelogram of the stationary time series. Here's our example of the ages at death of the kings of England. We've produced our parallelogram in this case for lags of 1 to 20 on the once differenced time series. We can see from this parallelogram that the autocorrelation at lag 1 exceeds the significance bounds, but all the other autocorrelations between 1 and 20 don't exceed the significance bounds. Remember, we're looking for the bars of the histogram to remain within this particular function. Okay, and since we had 1 of the 20 breach that barrier, we can say that can happen from sheer chance alone. Okay, so I don't think that that we're having an issue in terms of the differencing equaling 1 in this case. Now for our example of the ages at death of the kings of England, looking at our partial autocorrelation function, we plot the partial parallelogram for lags of 1 to 20 for the once difference time series of the ages at the death of English kings, and we get the values of the partial autocorrelations. The partial parallelogram shows that the partial autocorrelations at lags 1, 2, and 3 exceed the significance bounds, are negative, and are slowly decreasing in magnitude with increasing lag. So lag 1 is minus 0.36, lag 2 is minus 0.335, lag 3 is minus 0.321. The partial autocorrelations tail off to 0 after lag 3. Now that we spent some time evaluating the parallelogram and the partial parallelogram, we need to select a candidate ARIMA or ARMA model. And ARIMA model is a PDQ model. ARMA is similar, except for it's just a PQ model. So what insights did we gain from looking at the correllogram and partial correllogram. Well, since the ACF is 0 after lag 1, and the PACF tails off to 0 after lag 3, this means that the following ARIMA models are possible for the time series of first differences. So we can have more than one candidate model in this example, and we're going to find that we have 3. We can use an ARIMA 3-0 model, which is an autoregressive model of order p equals 3, since the partial autocorrellogram is 0 after lag 3, and the autocorrellogram tails off to 0, although perhaps too abruptly for this model to be appropriate. You can use an ARIMA 0-1 model, that is, a moving average model of order q equals 1, since the autocorrellogram is 0 after lag 1, and the partial autocorrellogram tails off to 0. And finally, we can use an ARIMA PQ model, that is a mixed model with p and q greater than 0, since the autocorrellogram and partial correllogram tail off to 0, although the correllogram probably tails off to 0 too abruptly for this model to be appropriate. To decide which model to use, we're going to invoke the principle of parsimony. We have 3 models. We have an ARIMA 3-0 model, we have an ARIMA 0-1 model, and we have an ARIMA PQ. And what we're looking for here is the model with the least amount of complexity to it. Okay. Since the ARIMA 3-0 model has 3 parameters, it's fairly complex. The ARIMA PQ model has at least 2 parameters. It's also somewhat complex, but the ARIMA 0-1 only has 1 parameter, and therefore we're going to use the ARIMA 0-1 model as taken as the best model. Since an ARIMA 0-1 model with a p equals 0 and q equals 1 is taken to be the best candidate model for the time series of first differences of the ages at death of English kings, then the original time series of the ages of death can be modeled using an ARIMA 0-1-1 model with p equaling 0, d equaling 1 for our differencing, and q equals 1, where d is the order of differencing required. A moving average model is usually used to model a time series that shows short-term dependencies between successive observations. Intuitively, it makes good sense that a moving average model can be used to describe the irregular component in the time series of ages at death of English kings, as we might expect the age at death of a particular English king to have some effect on the ages of the death of the next king or two, but not much effect on the ages at death of kings that reign much longer than that. So there's going to be an impact close in between the lives of certain kings. But when we start looking, at a king that lived 300 years ago compared to a king that lived just 20 years ago, that the gap is going to be more significant from the one 300 years ago, and the relationship of the trending should be less significant as we span across that amount of time. So let's get into another ARIMA example. The volcanic dust veil index from the northern hemisphere from 1500 to 1969. This is a measure of the impact of volcanic eruptions, release of dust and aerosols into the environment. From the time plot, it appears that the random fluctuations in the time series are roughly constant in size over time, so an additive model is probably appropriate for describing this time series. Furthermore, the time series appears to be stationary in mean and variance, as its levels and variance appear to be roughly constant over time. Therefore, we do not need to difference this series in order to fit an ARIMA model, but can fit an ARIMA model to the original series. The order of differencing required d is 0 here in this case. We can now plot a correllogram and partial correllogram for lags 1 to 20 to investigate what ARIMA model to use. We see from the correllogram that the autocorrelations for lags 1 2, and 3 exceed the significance bounds, and that the autocorrelations tail off to 0 after lag 3. The autocorrelations for lags 1, 2, and 3 are positive and decrease in magnitude with an increasing lag. So lag 1 is 0.66, lag 2 is 0.374, lag 3 is 0.162. The autocorrelation for lags 19 and 20 exceed the significance bounds too, but it is unlikely that this is due just to chance, since they exceed the significance bounds, especially for lag 19. The autocorrelations for lags 4 to 18 do not exceed the significance bounds. We would expect 1 and 20 lags to exceed the 95% significance bounds by chance alone. From the partial autocorrelogram, we see that the partial autocorrelogram at lag 1 is positive and exceeds the significance bounds, 0.666, while the partial autocorrelation at lag 2 is negative and also exceeds the significance bounds of minus 0.126. The partial autocorrelations tail off to 0 after lag 2. So when talking about selecting a candidate ARIMA model, like before, since the correlogram tails off to 0 after lag 3, and the partial correlogram is 0 after lag 2, the following ARIMA models are possible for this time series. We have an ARIMA 2 model, we have an ARIMA 03 model, and we have our ARIMA PQ mixed model. Invoking our principle of parsimony, we look at ARIMA 2.0 model having 2 parameters, ARIMA 03 having 3 parameters, and ARIMA PQ having at least 2 parameters. Therefore, we can say that either using an ARIMA 2.0 model or an ARIMA PQ model are equally good candidate models. If an ARIMA 2.0 model with P equals 2 and Q equals 0 is used to model the time series of volcanic dust veil index, it would mean that the ARIMA 2.0.0 model can be used with P equals 2, D equals 0, and Q equals 0, where D is the order of differencing required. Similarly, if an ARIMA PQ mixed model is used, where P and Q are both greater than 0, then an ARIMA P0Q model can be used as well. An autoregressive model is usually used to model a time series which shows longer-term discrepancies between successive observations. Intuitively, it makes sense that an AR model could be used to describe the time series of volcanic dust veil index, as we would expect volcanic dust and aerosol levels in one year to affect those in much later years, since the dust and aerosols are unlikely to disappear quickly. Now we're going to get into some examples of forecasting using ARIMA models. So let's go back and take a look at our example of the ages at death of the kings of England. Once we've selected the best candidate ARIMA PDQ model for your time series data, we can estimate the parameters of the ARIMA model and then use that as the basis for our predictive model to create our forecasts. For example, we discussed that an ARIMA 011 model seems a plausible model for ages at deaths of the kings of England. We can plot the observed ages of death for the first 42 kings, as well as the ages that would be predicted for these 42 kings and for the next 5 kings using our ARIMA 011 model. Now, we're not limited to just 5 kings. This is just what I had specified in the model. As in the case of exponential smoothing methods, it is a good idea to investigate whether the forecast errors of an ARIMA model are normally distributed with mean, 0, and constant variance, and whether that these correlations are between the successive forecast errors. For example, we can make a correlogram of the forecast errors using our ARIMA 011 model for the ages at death of kings and perform the Lejeune box test for lags 1 to 20 by typing the following. The p-value for the Legendre box test is 0.851, indicating that there is little evidence of non-zero autocorrelations at lags 1 to 20. The parallelogram shows that none of the sample autocorrelations for lags 1 to 20 exceed the significance bounds. Also, the p-value for the Legendre box test is 0.9, which we can conclude that there is very little evidence for non-zero autocorrelations in the forecast errors at lags 1 to 20. We can check whether the forecast errors have constant variance over time and are normally distributed with mean zero by making a time plot of the forecast errors and a histogram with overlaid normal curve. The time plot of the in-sample forecast errors shows that the variance of the forecast errors seems to be roughly constant over time, though perhaps there is a slightly higher variance for the second half of the time series. The histogram of the time series shows that the forecast errors are roughly normally distributed and the mean seems to be close to zero. Therefore, it is possible that the forecast errors are normally distributed with mean zero and constant variance. Our conclusion is that since successive forecast errors do not seem to be correlated, and that the forecast errors seem to be normally distributed with mean zero and constant variance, the ARIMA 011 model does seem to provide an adequate predictive model for the ages at death of English kings. Now that we've gone about this, let's go ahead and dive into a practical application example. We're going to forecast product sales quantity. Before we begin, let's go ahead and first try to understand a little bit about the data set we're working with. This is a very common example that we're going to see in business applications where I have sales of a product over a given span of time. So in this case, I'm looking at just two pieces of information: the time, represented in months, and the quantity of a particular product. So what does this time series graph show us in terms of the modeling technique to use? By looking at the shape of this line graph, do we see any patterns? Is there a trend? If so, is there any direction? Is there seasonality in this chart? And what potential models would we use for this application? Well, one would be Holt-Winters exponential smoothing, and another would be an ARIMA PDQ approach. Before we begin, let's first decompose the time series. Okay. So in order to further isolate which algorithm to use for this analysis, let's just look at these components. We see that the trend component, in this case, can clearly be shown as an upward trend that's stabilizing over time. Okay. There is a regular seasonal component that we see, which almost kind of looks like a little heartbeat pattern, going doo-doo, doo-doo. And there is a random component of the data, and this random component reaches a peak of 3,500 units to a trough of minus 4,500 units. The gap of the spread is wide enough that we probably should use an ARIMA PDQ model in order to capture this noise in our final analysis. So now we're going to go about differencing the time series. In this example, we're going to use a differencing of 1 and just see how the data looks. The time series of the first difference does appear to be stationary and mean in variance. Since we had to difference the time series once, and so the order of the differencing of D is equal to 1. This means that we can use an ARIMA P1Q model for our time series. The next step is to figure out the values of P and Q for the ARIMA model. There is a technique in R called auto-ARIMA, which will identify the best candidate ARIMA PDQ based upon some evaluation parameters. Okay, the default in this technique is the Akaki Information Criterion, or AIC. When we process this technique, the resulting model is an ARIMA 011. Now, please note that we can actually go and evaluate the ACF, the PACF, the Bach-Lejeune test, etc. using the techniques outlined in the presentation, but we will skip this evaluation for brevity's sake. Now that we've done this work, we can go about charting this line chart onto the graph. So we can forecast moving forward into a period and see the resulting product, estimated quantities. In our example, we extended the forecast out for an additional 12 months. The final forecast takes into consideration our seasonal variations, evolving macro and micro trends of this product, and it leverages the random noise when building the quantity estimates. The final estimated sales projections can be leveraged to determine procurement requirements, sales budgets and goals, etc., etc. Lastly, we'll talk a little bit about time series and using a generalized least square model. There are many instances where we are interested in not only predicting the development of a time series dataset, but we also want to understand how individual independent variables, x in this case, impact the dependent variable, y, spanning across time. For example, sales development over time taking GDP, unemployment rate, and other variables into account. So econometric analysis of time series data. We would naively initially approach this task using the standard OLS linear regression model with the form of y equals intercept plus beta 1 x1 plus beta 2 x2 plus so on and so forth, and finally the error term. And we get into a very detailed discussion about OLS in our regression tutorial earlier on. So if you need a refresher on those techniques, please feel free to check out that presentation. Now, one important thing to note is a critical assumption when building with OLS regression is that the errors are homoscedastic and serially uncorrelated. It is common when working with time series data that the errors are unlikely to be independent and are serially correlated. Therefore, it's important to understand that OLS regression will not be sufficient when modeling time series data. And this is an important concept because when we're working with regression, we're used to using OLS regression. We need to take a different approach when working with time series. In order to address the serial correlation issue, we can employ a generalized least squares model fit by maximum likelihood. This approach focuses on resolving some of the underlying concerns with the error term. There are substandard models for autocorrelated regression errors, with the most common being the first order autoregressive process AR1. The VT represents the random shocks and are assumed to be Gaussian, white noise, and phi represents the correlation component. What this is doing is it's taking the error term and it's breaking down the error term into two subcomponents. So you can think of this much like a proton in the atom, where it's made up of quarks. This error term in OLS regression just represents the difference between our observed and our actual value. But there are even fundamental components that are important to understand in time series. An AR2 model, on the other hand, continues this process, breaking the error term down, and we now see that we're taking phi 1 plus the error t minus 1 plus phi 2, the error term t minus 2 plus v of t. In contrast, in the first order moving average process, MA1, the current error depends upon the random shock from the current and previous periods rather than upon the previous regression error. So if I'm looking at an MA1 model versus an MA2 model, we can see the following. And finally, AR and MA terms can be combined in ARMA PQ processes. Therefore, an ARIMA or an ARMA 1-1 model is a hybrid. Now that we have a basic understanding of the GLS approach, let's work through an example. Here is the Hart-Nagel dataset from 1931 to 1968 of different macroeconomic attributes of women in Canada. And for those who have been following along the series, in our neural network tutorial, we touched upon this dataset there. But if you haven't seen it, and this is the first time you're looking at this dataset, I'll just go into a brief description of some of the variables. We have a variable that represents the year, a variable that represents the total fertility rate of births per 1,000 women. Then we get into some metrics that are related to individual women, such as their labor force participation rate, their post-secondary degree rate, indictable offense conviction rate, and then their theft conviction rate. And for control purposes, we also include some metrics related to men, such as their indictable offense conviction rate and their theft conviction rate. What we're trying to do is we're trying to estimate the variable F convict on TFR, partic, degrees, and M convict. And the rationale for including the M convict variable is to control for omitted variables that affect the crime rate in general. So let's go ahead and begin. Before we dive into the model itself, let's just take a look at the shape of our time series plot. Now, the data set does not appear to have any seasonality components. However, we could decompose the time series and seasonally adjust the data set to ensure that we're only focusing on the trend and random components. We talked about that seasonally adjusting earlier in the presentation, and that is something that we could do before we go about the modeling aspects. So we can incorporate other techniques into our time series work. So let's go ahead and first run a multiple linear regression. Okay. When we run this, the women's crime rate appears to decline with fertility and increase with labor force participation. The other two coefficients are statistically insignificant. The R-squared metric shows 0.6948, which is a fairly strong value and indicates that the model is capable of predicting a large portion of observations. And if you want to understand what these metrics mean, please go through the OLS tutorial earlier on regression analysis. In some previous tutorials, in our EDA tutorial and our regression analysis tutorial, we got into the concept of residual plots and how to detect errors within the residual plot. But now that we've created our OLS model, I want to show how we can use a residual plot to detect autocorrelation. If we look at this plot, we notice that the residuals are not uniform and they're randomly distributed across the zero line. This can be observed by the large peak and troughs that we see. Additionally, there seems to be a direction of the residuals that are moving upward, indicating that serial correlation is a problem and that this OLS regression violates statistical assumptions. So a general shape of the dots moving in a direction is a visual indicator that we can use for detecting serial correlation or autocorrelation. So when you're looking at residual plots, look for this pattern as well. Now that we've determined that OLS regression cannot be used in this case, we need to go about determining what model approach we should use. Like the examples before, we need to create the ACF and PACF chordalograms and examine them in detail. However, we need to look carefully at the patterns of each one to determine which model approach ARP MAQ or ARMA PQ makes most sense for the GLM approach. The reference chart that we have here can be used as a general guideline for this evaluation. So When you're looking at creating this regression analysis over time series, and you're not sure exactly how to evaluate the ACF and PACF, we need to go back and refer to this slide. Okay, this is very helpful for me, and when I first started working in time series, it was difficult for me to understand exactly what model I should be using where. Okay, so just remember, if I need to understand specific variables related to time series and decide which approach to use, come back to this slide. It will help you out. So I produce the correlograms, the ACF and the PACF, and I evaluate the spread across the lags. In this case, the ACF diagram shows an exponential decay to lag 2, or is a sinusoidal pattern, and the PACF shows significant lags before dropping to 0 at lag 2. This indicates that the ARP approach should be used, and the PACF showed a drop to 0 at lag equals 2. Therefore, we will use the AR2 model for our analysis. We follow up by computing the Durbin-Watson statistics for OLS regression. This function produces bootstrapped p-values for the Durbin-Watson statistics. 3 of the first 5 Durbin-Watson statistics are significant, including the first. This indicates that autocorrelation is present in the dataset and will be improved upon through non-OLS modeling methods. Okay, so when we suspect that serial correlation or autocorrelation exists, run the Durbin-Watson test. Now that we've produced the model, let's go ahead and take a look at the model fit for a GSL model. Some observations is that the phi1 is equal to 1.06835 and phi2 is minus 0.551, which is what we expect. We expect that phi1 is to be greater than 0 and phi2 to be less than 0. The MS, or the M-convict variable, was not statistically significant in the OLS model, but it is significant in the GLS model. So this just shows you that using a different regression technique can provide different insights in terms of variables and their statistical significance. And the Ikaki information criteria, AIC, is 305.41. And so lower values indicate stronger models. So if we're using this model over and over with different types of variables, we're looking for models that have a lower AIC. To verify that the AR2 model was the preferred model, we reran the models for AR0, AR1, and AR3, and then we performed ANOVA. And we got into the topic of ANOVA analysis in earlier lectures, the same lecture that has our linear regression analysis. So please refer back to that if you want a primer. And in this case, the AIC is the lowest for the AR2 model, 305.41, but followed very closely by AR3 at 307.40. So if we follow the principle of parsimony, the AR2 model is less complex and therefore should be used as our final model. And so let's take a look at our final GLS model. So here is an extract of the model fit and some statistics that we have here. Some additional changes are that we remove the intercept and the degree variables. And the Ikaki information criteria, AIC, is 304.59 compared to 305.41. Now that we have this, let's take a look at how our model fits. We can see the actual observed values with the blue line, and now we can use our GLS prediction using our orange dotted line. Furthermore, we actually have a regression equation we can draw from. So if we want to talk about how specific variables impact on this, we now have our conviction rate equaling minus 0.024 times the fertility value plus 0.304 times the labor value plus 0.10 times the male convict plus the error term. In this case, the error term is 1.154 times the error t minus 1 minus 0.53 times the error term t minus 2 plus v of t. Thank you for taking the time out to go through the time series analysis with me. I appreciate being able to walk through these concepts with you. If you have any questions or would like to learn more about other models or techniques, feel free to reach out to me directly or make comments on my channel. Thank you very much and have a nice day.